Welcome to my screencast on nuclear fission, chain reactions, and a nuclear power plant. So what we have here is a uranium-235 atom. And if I launch a neutron at it, you will see that the atom splits and 3 neutrons are released. So I'll do that one more time. And this is what we call fission, when the nuclei of an atom splits into 2 daughter nuclei. So if I only have one, you see something simple like what we just saw, splits, and exactly what we discussed happens. But what if I were to put 100 of the uranium-235 atoms on the screen? I will fire a neutron at it, and you can see that it's a chain reaction, and every single one of the uranium-235s will fizz. And so that you just witnessed a chain reaction. Now, if this were to happen inside a containment vessel, and I could get, and I have to make my vessel a little bit larger. Come on, there we go. So that it will hold 100. There we go. If this happens inside a containment vessel that may be made out of metal or something, we're going to have an atomic bomb. And we don't want that. Lots of damage done to Japan in Hiroshima and Nagasaki during World War II. So we want to get the power, the energy that comes off of the fission process, but we want to do it safely. So I want to show you some things that we can do. So I'm going to change this from a uranium-235 atom nuclei to a uranium-238. And when, let's see, is he going to do it? Oh, I'll just put a couple. So when I launch a neutron at uranium-238 atom, it just absorbs it, as you can see. So I'm going to launch it at another one. And when it absorbs it, the mass goes up and becomes a different isotope, uranium-239. And so there are some advantages to this, because if we have something in the material that can absorb the neutrons, the reaction will not get out of control and become a bomb. So I want to try some combinations here. So we did 100 uranium-238 atoms a moment ago. Now we're just going to do 75, and we're going to do 25 of the U-238 uranium nuclei. So I'm going to launch a neutron at uranium-235, and let's see what happens. We've got a chain reaction, and almost all of the uranium-235 were split or fizzed, but we do have one left right over here. So we were able to stop one of them from reacting by adding uranium-238 nuclei. So let's try, instead of this time, let's do 50-50. I'm going to take my neutron gun here. I'm going to launch it at a uranium-235. We have a chain reaction, but notice this time we have even more uranium-235 left over. And so the reaction didn't get as hot. Let's try one more combination. Let's do 25 uranium-235 and 75 uranium-238 nuclei. So I'm going to launch my neutron. Unsuccessful. Let's try again. And see that only one atom fizzed. That's not going to give us very much energy at all. Only one once again. So this combination really keeps the chain reactions from happening. Doing the best I can here, but I'm not having much luck. Let's see. I think I might be out of options. So you can see that this combination is very important. So what scientists will do is they will enrich the uranium samples for a nuclear reactor with varying amounts of 235 and 238 to control the reaction so we don't get a bomb in a nuclear power plant. So what I'd like to show you now is what actually happens in a nuclear power plant. So I'm going to start by just launching a neutron at these uranium rods that are in here. And over here we're going to see the energy produced in joules, and we'll see the power output in joules per second as the reaction occurs. And up here we also have a thermometer. It will show the temperature of the reaction. So it has begun. You can see the temperature is rising. The energy produced is increasing. Lots of power going out right now. This red and orange color means it's getting really hot. Reaction's kind of slowing down a bit, and it's starting to get really hot again. And it would be a bad thing if we had it get too hot, because we'd have a meltdown, which is not a good thing, because radiation will be released into the atmosphere, and the people who live around the nuclear power plant would be unsafe. So what they do in a nuclear power plant is they have control rods, and these control rods are made of something similar to the 238 that would absorb a neutron. So I want you to watch when I have the rods completely in. If I fire my neutron, you can see the reaction immediately stopped. It started over here, but it hit the rods. So I'm going to reset, and this time I'm going to do it with just halfway out, and let's see what happens. That also stopped it. So this time I'm going to start the reaction. When the temperature gets up into this gray range right here, I'm going to bring the rods in and try to slow the reaction down. So we're getting warmer, okay, and I'm going to put the rods in, and notice that the neutrons are being absorbed and the temperature is going down. Now I failed because I let the reaction stop, and we don't want it to stop. We still want energy, power coming out so that people can have electricity in their homes. So let me try it again. This time when I launch it, I'm going to make sure that the reaction continues. Okay, so I'm going to bring it in, and it's starting to slow down, so I'm going to take them out. Let the reaction keep going. Okay, we still got energy. Oh, it's starting to get too hot. So I'm going to bring it in, and it appears I was able to control the reaction to the point that I did not have a meltdown. And notice that it's still going. It's still fizzing. And that's exactly what I want. Okay, so we got almost all of the uranium fizzed, not all of it, but close to all of it. Looks like all of the neutrons are gone now. But I was able to use most of my fuel, my uranium fuel, to create quite a bit of energy. Thank you for watching my screencast on fission, chain reactions, and nuclear power plants.